So, good afternoon again, everybody. Thank you for being prompt. We're right on time, right on the money. That's how we want to do it. Thank you for that. So, session 2 of our 3 sessions today, we're going to be moving on to looking at human interaction with autonomy, and we have 3 speakers to give us some perspectives on that, and it's the same format as we've just done. So, we'll have 3 speakers, and then if you could hold your questions, write them down or keep them in your head, and then we'll come to a Q&A, 50 minutes of Q&A at the end before the next break, and then we'll come back for more of a round table at the end. So I'm delighted for our next speaker to welcome my old friend, with the emphasis on friend rather than old, Professor Tony Prescott, who wasn't listening but is now, Director of the Sheffield Centre for Robotics. Tony is Professor of Cognitive Neuroscience and Director of the Sheffield Centre for Robotics. It's a cross-institutional robotics facility with over 100 active researchers. His research focuses on the development of biomimetic robots, control systems modelled on the mammalian brain, human-robot interaction, and assisted robots. He's also developing a number of commercial robots, including a robotic table and a biomimetic robot companion, which some of you will have seen, I think, and has some interesting business models around magazines for that one, which I think is a throwback to my youth anyway, so that's quite innovative, I think. Anyway, Tony's going to talk to us about designing robots for human, physical and social interaction. Tony.
Thank you very much, David, and thank you to the Royal Academy for the invitation. It's a real joy to be here. I want to tell you a little bit about the work we're doing on human and physical social interaction, but also about the motivation for it. So that's what I'm going to try and cover in my 15 minutes. So Sheffield Robotics, David's given us a nice introduction. We are actually both universities of Sheffield under this umbrella. We also include, as one of our partners, the Advanced Manufacturing Research Centre, which is between Sheffield and Rotherham. And really what we want to do is to grow Sheffield as one of the locations for this new frontier of innovation and industry in the UK, building, of course, on our great, magnificent past in UK industry and steel. We used to be known for steel and cutlery. We'd like to be known for robotics. And we don't see any reason why not. We've got a massive amount of skill in Sheffield, and one of the largest faculties of engineering. I think we recently went ahead of Cambridge in terms of research income for engineering, which our Pro-Vice Chancellor is always proud to tell people about. So we have lots of themes of research, and I'll only briefly cover 1 or 2 of them today, but please ask me afterwards if you're interested in these other areas of research. I'm particularly interested in the assistive, the cognitive, the biomimetic, and the companion robots, but we also do work in particularly manufacturing, swarm robotics. Field robotics is a big growth area for us. We just took over an aircraft hangar in what was formerly Sheffield Airport, where we're going to be able to fly drones without dropping them on anyone's head. And we're also interested in mixed reality telepresence. So these are some of the people we work with. There are a number of companies up there, and if there are company reps in the audience, we would love to also count you as a partner in some of our projects. So I want to talk about the potential for assistive robots, and the potential really arises out of a societal need. So the House of Lords recently, I think this is going back a couple of years, looked at the issue of UK population ageing, and most people have heard the facts here, but we are, like the rest of the developed world, looking at a situation where the number of older people is increasingly outnumbering the number of younger people, and we haven't yet thought how we're going to cope with this situation. The conclusion of the Lord's report was that we are at population ageing rapidly, but the government and our society are woefully underprepared. And there are many things that we might want to do about that. And what I want to, this is just a picture showing you the demographic situation. Basically, the situation is there are going to be more people in this top area here between 65 and 100, than there were up until now. So we're shifting from a situation where the number of people that are 60 plus is going to be much larger. By 2060, one working person for every dependent. The ratio right now is more like 3 to 1. So this is really a dramatic change. And as we get older, sadly, we're also more likely to have disability. So 20% of those aged over 70 have some disability, 50% of those aged over 85. And you can look at the economic projections, and those are pretty frightening too, that our bill for social care is going to increase annually by 10 billion per every additional million we have over pensionable age. And our bill for social care is going to treble, I think, in the next 20 years. So dealing with this issue requires societal action on many different levels, and technology is only one small part of the answer. Actually, I think technology could be very important and very useful, but there will be resistance to that, and I'll return to that later. And partly the resistance is based on a misperception of what this technology is good for, and I think that's why we need to advocate for the use of technology and to educate people about what it can actually do. Why would robots be useful as we get older? Well, the reason is that a lot of the challenges we face are physical ones. So we already have a revolution, if you like, in telecare, where we deliver a lot of social care now via computers and via the internet, but of course the computer can't physically intervene in your home or in your residential care setting to help you. These are the problems we're likely to have as we get older, and these are the ones which are, have a physical element. And so actually helping us physically is something that technology cannot do unless it has actuators, and that makes it robots. But a lot of the problems we have as we get older are also more psychological. So we shouldn't forget the psychological side of this. These are actually the top 36 reasons why people leave their own home and move into residential care or a hospital. And the first 10 of these are actually more psychological. Number one, their fear of falling is the reason why people leave their homes. You can see others here sort of feeling lonely. Abuse, bereavement, cognitive impairments, a big one, depression. So it's not a very cheerful list, but this is what we've all got to look forward to. And something that can make us more positive about this is actually, if you are able to stay in your own home longer, then you will be happier. There's a potential win-win situation that assistive robots could help people live in their own homes for longer of their life, and I think also be happier there. So it's about helping people be independent. And of course, there's lots of stories all the time about how this impacts on individuals. The stats are scary enough, but the individual stories are also quite tragic. This is one where a famous prima ballerina who had a stroke, and this was in the news a couple of years back. It particularly caught my attention because she was being forced to leave her own home because she couldn't go to the toilet by herself at night, and social care wouldn't pay for her to have a helper to go to the bathroom. And so this is the sort of challenge where I think robotics could actually help. We have to be imaginative in thinking of the right kinds of solutions, but we could transform people's lives with technology and help them be more independent, live for longer in their own homes. It's a potentially win-win. And finally, on why we should do this, the UN says we should do this, that if there is an opportunity to help people with disability by developing new technologies, then we should do that. We should do it taking into account of cost, making sure these things are affordable. We don't want to create a two-tier society, some people having robotic help and others not. So I think we have the opportunity in the UK and in Europe particularly to be at the vanguard of this. We have a lot of support, for instance, from the European Union, and we have in the UK the National Health Service, which an integrated health service could be a real vehicle for helping to push these out to end users. So lots of ways that robots can help carers. One is to address the skills shortage. There is already a skills shortage. Heard about it again today on the radio. There's a problem with these new rules about people coming to this country to work, which means that I think we're going to end up sending back some trained nurses, and we're going to have more gaps in our nursing profession, we can help carers. We don't want to replace carers, we want to assist them with suitable technology. We can make carers more efficient, and we can help older people help each other, because if you think about it, a lot of people who are older don't live on their own, they live with another older companion. We had some great stuff from Michael earlier with his PR2, which is kind of a humanoid robot platform. And humanoids are great for developing these technologies, but I don't think we are going to have a lot of humanoids in our homes in the near term. One reason is that they're expensive. Another reason is that maybe perhaps people don't really want them. And a third one is that there are other ways of solving the problems. So once you've looked at the challenge and understood it properly, you might want to design a piece of technology specifically to suit it. And of course, we already have robots in our homes. The one that maybe most people have is actually this one. Automatic washing machine is really a robot, particularly the latest ones that decide what wash cycle to run, how long to clean the clothes for, how long to dry them for. That's really a robot. It has sensors, it has actuators. And people say, I don't want a robot in the home. I say, well, you've really already got one. And many people have got this too. And apparently 40% of people who own a household vacuum cleaner robot have given it a name. And I find this hard to believe, but apparently 30% take it on holiday. So people not only have these robots, they actually like these robots. And I think that's the theme I might come back to. And there's Pepper, again, sort of more human-like, but with a sort of a base that wheels around. This one is for ironing clothes from Siemens. And that, of course, is an intelligent toilet, which you see a lot of in Asia, but very few here in the UK. I want to talk a little bit about this, which is a device I'm developing with Sebastian Conran. We've heard about driverless cars already, and there's various other assistive robots on the horizon. It's not just about robots that do their own thing. There's also some very specific, direct and intimate ways in which robot can help us. This is Cyberdyne's assistive walker. And we recently went on a trip to Japan and visited Cyberdyne. I think these sorts of exoskeleton devices will be useful in enhancing people's mobility. And this is a technology that is, I think, maturing very rapidly. And that certainly we're starting to see these in hospitals. We're testing them in Sheffield hospitals, and we might see them on the streets soon. So with Sebastian Conran, who is a designer in residence at Sheffield University, we've been thinking about how to build assistive robots that people will actually want and that will be attractive to them and will be non-threatening. And we came up with the idea of, well, what about a robot table? Because if you have mobility issues, then it would be useful if the robot came to you rather than you went to the table. There's a lot of overbed tables that people have if they have poor mobility that fit over your bed in hospitals or at home. And we thought about how about an intelligent overbed table which could come to you when you need it, and when you're finished with it, it goes back and recharges itself. So this was an Innovation UK project. This is the kind of the latest prototype device. It's got various degrees of freedom of movement. It's got a navigation system which currently works with beacons on the ceiling. We're looking to replace that with a purely visual-based navigation system. And it's really a platform, but it's a platform that we think people will find appealing and non-stigmatizing, because a lot of assistive technology is a bit of a badge. Oh, you have mobility issues, and people don't want it. So, but this, working with an industrial designer like Sebastian Conran, we hope actually something like this could be something that might be in your executive office. I've got an intelligent table, and therefore people will feel happy to have these things at home. It's about improving independence, and there are various scenarios in which you could imagine taking this platform and adapting it to different uses. And if anyone wants to talk to myself and Sebastian about where else we might deploy it, then please come talk to us. We've recently started a spin-out company, and we're interested in investors, so we'd like to have that conversation too. And of course, something we'd like to do is to put an arm and a gripper on it. The kind of thing that Michael's robot's doing would work very well on this robot. So we're looking to design a lightweight arm that can pick up objects and move them around and so on. And perhaps, so the goal, and we've applied to the European Commission for funding to do this, is for the table to go to the kitchen, perhaps prepare some food and bring it back to you and serve it to your bedside. So one of the big challenges here is to actually physically interact closely with people. That list that I showed you earlier of the problems people have, a lot of those are problems like dressing, toileting, bathing and so on, where you have to get very close to people if you're going to be able to help them. And that is a challenge that I think we've yet to adequately address in robots. You know, we can interact with objects, but physically interacting safely with soft, fragile things like people is still a big challenge. I wanted to mention Etienne Burde at Imperial College here in London, because he's doing really great work on human-robot physical interaction, and he's actually looking at how robots and people can work together on joint tasks, which is something that you might want to be able to do, is to actually assist directly somebody who's trying to do something that they can partly do themselves, but not completely. So depression, cognitive impairment, they're on the lists of reasons why people struggle at home. And this is the Jibo robot. Some of you may have seen publicity around this. This was a Kickstarter initiative from MIT, Cynthia Breeziel. I think they raised, or have raised now $10 million or thereabouts. So this is a robot that sits on your kitchen table, and it's able to relay messages to you. Its main robotic function is actually swiveling around this base, and it can look at you and orient. So it's a fairly minimal robot, but it's the beginning of what we might think of as companion home robots. Do we want companion home robots? Well, this is one of the most controversial aspects of this, because people think, well, what if I have a robot? Does that mean my children will never come and visit me again? I think that that's an open question. We already have situations where people have almost minimal social contact anyway. The average visit time in UK social care is 15 minutes, and that's somebody coming into your house and they have to help you to go to the bathroom, prepare some food for you, perhaps say a few words, and that's all you get in a day. So we're not talking about a choice between a lot and less. We're talking about a choice between very little, and perhaps complementing that with some other form of social interaction. If we think about the social interaction that we have with a radio or a television set, we're already socially interacting with pieces of technology or with other people via our pieces of technology. So I think of a robot as potentially providing some companionship, not replacing human companionship, but supplementing it in the way that perhaps a pet can supplement your companionship. And we all know that actually having a pet helps you stay happier and live longer. It's not always practical to have a pet. The Japanese have developed this robot seal called Paro, which is fairly limited in its robotic functionality. It's particularly designed for use with people who have Alzheimer's, and it's engaging, and one of the things it does is it provides a social bridge. It helps your relatives come to visit you. It gives them something to talk to you about. We're working on a companion robot, which we're demonstrating a prototype out here, and this is currently designed as an education entertainment robot, but what we would like to do is develop this towards something like a robot pet that you could imagine also being an assistive aid for people living alone, and functions like reminding that you maybe should take your medicine or phone your daughter could be things it could do. But just providing some companionship, I think, is not something that we should think robots can't do. I think they can actually help to fill a little bit that gap. And one of the things that they can do is that a robot, by giving you more confidence, could actually help you have the confidence to go out and talk to people. Am I really out of time? Yeah. Let me just quickly show the video, and we can talk about
what is it that connects us? We learn as we live. We get happy. We get sad. When we're tired, we recharge our batteries. Now there's an artificially intelligent robot that you can build, program and connect with. Miro, developed by leading robotic scientists. Learn about the world of robotics and connect with Miro, your unique biomimetic robot. Build Miro every week. Part 1 out now.
So that's the commercial break. Part 1 actually out in January, I hope. So watch out for the adverts. My very final thing, I want to say is that you may have watched Humans last night, you may have watched iRobot straight after. So we're in a situation where Stephen Hawking, Elon Musk, everybody is warning about the risks and threats of AI. This isn't a new issue. It's been around forever. I love this quote from John Baudrillard. The theme of slavery is always bound up with the theme of revolt. The robot, like the slave, is both good and perfidious, good as a captive force, perfidious as a force that may break its chains. So we worry about robots. The ancient Greeks used to worry that the statues would come alive at night and kill them in their beds. We've been worried about robots ever since we had started to build them. But I think we are now in a situation where AI is progressing very rapidly, and the fears have to be considered and addressed. And I think something like the Royal Academy should have a position on this, because we ought to be able to answer those questions. We have a workshop at the Science Museum on Wednesday. I'm afraid it's already sold out. It shows you the popularity of these issues. But certainly I think we need to think about the ethical implications of the work we do and how to address people's concerns. Thank you very much.
Thank you, Tony. That was quite illuminating and humorous. It's great to see the ambition for the Sheffield Centre for Robotics beyond the centre and steel and the full Monty, which is the last thing we discussed, which is Sheffield is perhaps famous for. I think there's some very thought-provoking things there about whether AI is ready, and I think that's something we might get into a bit more when we get to the roundtable session. Anyway, our next speaker is, again, my friend and colleague, Professor Maria Fox, from the Professor of Computer Science at King's College London. She's had an illustrious academic career, which I'm not going to run through here, but she's currently Editor-in-Chief of AI Communications and Associate Editor of the Artificial Intelligence Journal, and a member of other... she's going to be the chair of the European Conference on AI next year. Her research is in automated planning, subfield of AI. She's been involved in developing some of the best-known modern approaches to temporal and metric planning, and has led a number of applications of planning to problems in robotics and industry. And in fact, we've worked together on a couple of different projects in autonomous underwater vehicles, and we've got deliverables to produce right now for one of the projects. So Maria's going to talk to us today. Her title is Choosing Precisely When to Do Things Can Really Matter. Maria.
Hello, everybody. I'm going to talk about, as David said, automated planning, and particularly in contexts when timing is critical. So, timing is critical here. So, we all know from the talks we've heard that we're going into a future where there will be many autonomous robots in all aspects of our lives, including transport, manufacturing, maintenance, healthcare, tourism, and many other areas of our social and economic infrastructure where currently we don't see very much in the way of autonomous robots. And the sorts of reasoning that future autonomous systems are going to require is going to be goal-directed, strategic, temporal, and resource-constrained. And the question I'm going to talk about today is, what can we add to robotics and control to achieve these sorts of objectives? And the answer is, in my view, AI planning. Okay, so how is planning different from control? Well, I completely agree with what Michael said earlier, that autonomous systems, the key to autonomous systems is knowledge. So planning searches among alternative sequence of actions, where actions are models of what can be done and what the effects are. And we use inference to allow us to think about the effects of actions and how to exploit those effects. And we might apply an action at some point in time. Let's say it has some effect P, and we want to exploit that effect P much later in time. So we're making decisions about what we can do now to have these later effects and exploit them. And we're searching these extremely large combinatorial spaces of alternative action sequences. So as well as inference, we need another tool, which is relaxation. Relaxation allows us to abstract our knowledge about the world and reason over these very large state spaces very efficiently. So an automated planning system uses search, inference, and relaxation in order to search these enormous, possibly infinite state spaces. And the outcome of the autonomous planning process are these causal chains of actions that achieve desired future states. So I want to give you an example of a project we've done on planning the timing of actions. So this is a situation where timing is really critical, and it's planning to efficiently manage multiple independent batteries. So just to take the example that we used to motivate this project, a soldier carries about 10 to 15 kilograms of batteries to power all his mobile devices in the field. And the problem we were interested in is, given some expected load over a time horizon, we want to maximise the extraction of charge from these batteries in order to minimise the number of batteries that are needed. And for the soldier, that's very important because that translates into the weight that the soldier has to carry into the field. And of course, we can generalise this idea to any situation where you've got a large number of batteries that can be loaded independently. And in order to model the problem, we exploit the fact that batteries have a sort of recovery behaviour, which comes from the fact that lots of the charge of a battery is bound up in its chemical properties, and you have to allow the battery some time to rest in order to release that charge so that it can be exploited. So if we capture that property, then the decision the planner has to make, remember we're talking about an automated reasoning system, is when should a battery be loaded and when should it be rested in order to allow it to release its bound charge. And if we look at this little animation here of a two-battery system, if we model batteries in terms of their bound charge and their free charge, then we can see that if we load a battery, then we consume its charge. And what we now need to do is switch the load to the other battery in order to give the first battery time to recover so that we can then switch back to it and consume its charge. So we want to automate this reasoning. And the way that we do this is we start with a mathematical model of the actual dynamic processes of the battery behaviour. And for the project we did, we used this kinetic battery model, which comes from the engineering literature, that actually represents batteries in terms of their bound charge and their free charge and the conductance. And the planner is going to decide when to load and when to rest each battery, as I said. And what it has to do is it has to search for a non-uniform discretization of the timeline. And the reason we care about a non-uniform discretization is because if we choose any uniform discretization for the problem, it's going to be so fine-grained that we're going to get a massive state explosion and we won't be able to get a scaling solution. So what we want to do is to find a discretization of the timeline that leaves long periods of time when nothing much is happening and other periods where you're doing lots of decision-making. So what we've done to solve this problem is we have this continuous model, and then we pick some quite coarse discretization, and we use our automated planner to solve the problem that I mentioned of managing the charge extraction over the time horizon. And then we validate that solution against this original continuous model, and then we go round this loop, this discretize, validate loop. And as we go round it, we're refining the discretization around the trouble spots that were spotted by the validation process. And what's nice about this is that we can plan for many sampled loads, and then we can synthesize a robust plan-based policy using machine learning techniques that will work for any given load. So we now get a very compact policy that manages these multiple battery suites very efficiently for any given load. Now, this is results taken from physical and simulation trials that we did. On the left, we've got a physical trial involving 2 batteries, where this is just one of our tests. We compared our plan-based learned policy with a standard alternating policy from the engineering literature, where you're just switching between the 2 batteries. And what we found is that we get about an hour's more charge extracted using the plan-based policy, and also critically we get reduced switching. And this is very important because switching is energy inefficient. Obviously it's something we want to avoid doing too much. So on the right there we have a little simulation which shows what the execution of our plan-based policy on a suite of 8 batteries. As the batteries go pale, that's because their charge is being consumed, and what you see is that switching action, which is the batteries are being switched according to the schedule determined by the planner that will access the most charge from them. Okay, now this is the plan-based policy learning method that I mentioned. It's a general method. We can apply this to many different problems, and I'll show you another one in a second. But what we do is we do offline training of the policy by generating lots and lots of sampled instances of our problem. So in the battery case, the sampled instances are sampled load over horizons. And we take lots of these, and for each one, we plan a really good solution to it. And then we take all of those plans, and we use machine learning decision tree classification to extract a policy, which is then a very efficient little representation that compiles in all this planning knowledge. And we use that policy in order to actually manage the batteries. And just to show you the generality of that approach, this is another problem where we were using a plan-based policy to guide an AUV around this moving harmful algal bloom in the Monterey Bay. So these things, you may know, they're massive patches that move over the surface, and they have quite a dispersed edge, so it's quite difficult to use a sort of reactive tracking method to follow them. So what we did instead was we sampled lots and lots of patches from the statistical models, and then for each of those we planned a really good solution to tracking its edge, and then we did one of these decision tree learning examples in order to compile that plan knowledge into a policy. We put the policy on that Dorado class AUV, and we then did trials in the Monterey Bay. And what you see on the right there is a graph that shows that under the guidance of the policy, the AUV was able to follow the edge of one of these patches, an unseen one, quite successfully over the 6-hour period of that mission. Okay, so this is a completely different example of when timing matters in planning. This is a search and track where what you have here, you can see there's a drone that's trying to follow a little red target that's on the ground there. And when its scan goes to 180 degrees, that means it's lost it. Now, when it can see the target, there's no planning required because it's a reactive problem to just follow the target. But in other cases, intelligent search is needed. And what we do is we use a motion model of the target to place these search patterns over the search area, and each search pattern has a time-dependent reward. And then the planner decides which subset of these patterns to actually search and in what order and at what time points. So what you now see is that the drone is executing this first spiral search pattern, and it goes around that search pattern looking for the drone, but it won't necessarily find it because its sensor is quite noisy, and also it's searching an urban space. That grey shadowed area is an urban space, so the target can easily get lost. But what the planner has done is it's decided exactly when each search pattern should start, and it put in a little holding pattern just here on this corner for the drone to execute before starting a rectangular lawnmower pattern, which it's now executing. So I don't know if you can see the target, but it is in there. It's moving around in, I can't get the thing. It's the little red spot that's moving in that rectangle, and the drone should be able to spot it, but it still can't because of the environment being too cluttered. So what the plan says is, well, if that search pattern fails to reveal the target, then it will go into the next search pattern. And the next search pattern is a perimeter search over a no-fly zone. So the drone is now going into that, and it flies around that perimeter and points its scan in towards the no-fly zone to search for the target. The target's kind of progressing through there, and the drone's having a pretty hard time finding it. So the planner has decided that it should search twice around this perimeter before abandoning it. And after it's searched that perimeter, if it still hasn't found the drone, then there's another search pattern that you can see going off to the side. Now, you might think, how is that search pattern in the plan? Why did the planner put it in there? The reason is because the planner has a hypothesis about where the drone is likely to be going. And that comes from the road network that's on this map. You can see there's a major road heading this way. So the drone would head that way if it didn't find the target, but actually in this case it has now found the target on that perimeter search, and it's back to tracking. Okay, so timing is very important in that application because we needed to know exactly when to search the patterns to get the maximum reward from them. Here, what you see here is a little simulation from our Pandora project that David was just mentioning, which is two AUVs coordinating together to do a task. And timing matters here because these two are going to coordinate to observe part of an underwater structure. And the planner, you can see the plan here on the left, has decided that they need to be in the same place at the same time over a particular temporal region in order to perform that operation together. One is illuminating the area and the other is observing the pillar. And once that observation is complete, then the observing vehicle moves away and their coordination is no longer required. And the plan goes on. There are many other tasks that one or both vehicles have to complete. Up here on the right, you see a fragment of one of our field tests. This is just one AUV performing that inspection mission. I don't know if you can see it very clearly, but there is a pillar there that it's inspecting. And the exact same planning and plan execution architecture that we use in that project, we also use in this other EU project, which is called Squirrel. It's to do with tidying a child's room. And the planner has to plan all of the activities involved in tidying the room, including planning to interact with the child. And here the planner has told the robot to attend to the child. The child is in the room pointing to where he or she wants toys to be put. So the planner has planned in these interactions with the child. That's the only bit of human interaction in my talk. And now that task can be completed. And then this one is another field trial from our Pandora project, where what you've got here is an AUV with an arm, which is about to execute the task of turning a valve. And what the planner has done is to arrange for the AUV to be at the valve panel, ready to do that valve turning operation as part of a longer mission involving many actions. Okay, so as a last example I want to show you of when timing really matters, this is another project we're doing where we're looking at using a planner to maintain voltage within bounds over time in an electrical distribution network. So what we have here is a fragment of a real distribution network, and voltage has to be maintained within safety bounds over a long horizon. But we also have a demand profile that is a predicted profile that it also extends over a long time horizon. And the thing is that if we don't act at all, if no action is taken, then there will be violations of the voltage constraint in the network as the demand changes. So what the planner has to do is it has to anticipate when these violations will occur, and it has to decide which actions to apply, which are stepping up and down transformers, turning capacitors on and off and so on, and where to put them on the timeline in order to anticipate and diffuse these violations. So what we have is that the planner looks ahead over time to anticipate when these violations might occur and to respond to them by putting in the appropriate actions. And the critical thing is exactly when should these actions be employed to keep the voltage within the bounds. Okay, so my conclusions are that timing is critical in autonomous systems, just as critical as knowledge, and future autonomous systems will need to plan strategically long missions involving lots of complex activity, sometimes cooperating with other systems to achieve complex goals, and crucially anticipating the consequences of their actions and the consequences of external events over time. So planning is needed to choose not just what to do, which actions to apply, but precisely when to do them. Okay, thank you very much.
Thank you, Maria. That was very interesting, informative. Good to see Pandora being used. That has real potential, I think, in the future of the oil field and the way marine robotics goes. Maria's also been a little modest with her own commercial ambitions, which I won't talk about here because it's probably very top secret, but there is some commercial stuff going on in the background, so she's well able to talk about the innovation aspects in more detail if you pin her down afterwards. Yeah. Right, so what we're going to do now is move into another Q&A session, a bit like we had last time. This is the moment when, if you've got burning questions you want to ask, now's the time. So I'd like to invite Tony, Maria and Jack back up onto the stage here, and we'll do 10 or 15 minutes of Q&A around the themes that we've seen on human-robot interaction and the evolving relationship between people and technology, which I think is something all of our speakers have touched on. So who would like to ask the first question over here? Please just announce who you are and perhaps let the girls get in with a microphone so that I guess we get it on the video. I think that's the reason. Yeah.
Hi, I'm Joanna Bryson, the University of Bath.
Yeah.
I'm going to ask Tony the question first, but the other two speakers might want to get involved. But Tony explicitly showed a cute robot video, a cute robot toy that says it's happy and sad and sleepy. The EPSRC principles of robotics say that the machine nature of a robot should be transparent, and this is to do with the ethics of getting these robots into our house. And there's a particular issue with these things that children might be telling all their secrets to, and you know, in the case of the Jibo robot you showed, they're saying that it'll be uploaded into the cloud. You know, Mattel's new Barbie robot is not only storing things in the cloud, but predicting, planning what the children will want to hear the next day and bringing it back. So I think there's a lot of issues. You guys, you mentioned ethics, but I would like to hear all of you talk about, as these devices come into the home, specifically the home, I know there's lots of different issues. What are you thinking about in terms of ethics? You have startups, how are you handling this?
So I should respond particularly for Miro. So I don't agree with that particular principle. I think that we deal with fictional emotions all the time. And every time you watch a movie, you're experiencing fictional emotions. You're caring about characters who aren't real in the world. And they're expressing emotions which are fictional. And the same thing happens with toys. And when we're young, we have toy animals. You might have dolls. And they have fictional emotions too. And I think actually dealing with fictional emotions in an educational setting is a way of learning to understand about emotions.
So how are you making it clear that the emotions are as fictional as they are in a character in a book or a movie? When it's a robot that's in the child's home, how are you making that as transparent?
It's clearly a robot. You look at it, it looks like something that isn't a real animal. But I would also say, okay, well, what is happiness, sadness? You know, if your robot has drives, if there are things which give it reward, and it does something and it achieves something which was a reward for it, why shouldn't it express an emotion? So there's a deep question there about what's fictional.
You're not sure whether or not these are artificial.
No. I have a view. I have a view on that, which is I think that our emotions are mechanistic processes too. And we can have a theory of emotions, and we can't build human-like emotions into robots. But we can build responses into robots which are similar to the kind of emotional responses that some animals have. Darwin wrote a great book on emotions, and he showed that our emotional expressions are actually shared with other animals as well. And they arise out of biological processes. So I think we can actually create things in robotic systems that have the same consequence and the same meaning as emotion. And then if we build those in a robot, and ours is a biomimetic robot, it has substrates which are modeled in the mammalian brain. So, you know, it's difficult to say at what point do those emotions mean something equivalent to animal or human emotions.
This is clearly a hot button topic, which could go on some time.
Yeah.
Would any of the others like to comment on Joanna's questions? No?
Well, I don't know about emotion. My work in planning is not directly connected to human-robot interaction, but certainly we do come across this issue of ethics in planning. So one of the things I can think of that's related to this is we've done some work looking at consumer demand and trying to help plan electricity use for collections of households. And privacy is then the issue. People don't want to share their data. They don't want to make clear when they're using the shower or something like this. And people get extremely concerned about data being stored that might be interpretable in terms of their own activities. So I think that that's where ethics comes up for us. But in fact, the data is very abstracted by the time we start doing any kind of aggregate modelling with it. So it's not actually a real issue, it's a perceived issue. And yeah, I think it's to do with getting people to understand how you're using data, what can be interpreted in terms of individuals' behaviour from it, and trying to avoid people being unduly concerned about that.
Okay. Jack, do you want to add anything, or you
I'll leave
don't
this
have
to the professors.
Okay, they're very smart. Okay, thanks. This is, if you want to have a good discussion afterwards in the reception, I would hang out with Joanna and Tony. Right, find out wherever they are and come along and join in. Okay, thanks for the question, Joanna. Great. Yes. Yeah.
Hi, Katya from ENT magazine. Question for Tony. So there's been some talk about robot dogs in Japan, IBA dogs, dying because, well, dying so to speak, because Sony is not repairing them anymore, and some people are getting really, really attached to them and really sad that now they're not able to repair their dogs. And they've been taking them around on travels and taking pictures with them and really getting attached to them. Are you addressing this issue in any way?
So I think people getting attached to technology is nothing new. I know people that are very attached to their cars, very attached to their phones. So to get attached is something which is unavoidable. If it's a nice piece of equipment and it becomes personalized to you. We are looking at attachments. Actually, one of the things we're studying is the ways in which people become attached to objects and the risks associated with that. So companies also, of course, want you to become attached to their object, although not to the point where you don't buy a new one, but certainly to the point that you'll want to, spend more money on it. There are different forms of human attachment, and we should distinguish between attachment to objects and attachment to animals and attachment to people and particularly attachment to caregivers. So when psychologists talk about human attachment, they're often talking about the bond between a child and its mother, which is a very important form of attachment. But we have also lots of other forms of attachment to other people, which are social bonds. We have attachment to animals. We have attachment to objects. And the question is, with things like robots, which are so lifelike, where do they fit in within that panorama of different kind of social relationships? It's natural for us as humans to engage with technology as though it has intentions, as though it has personality and emotions. I think it's unavoidable. I mean, Joanna might not want people to do that, but it's kind of what we do, and people are writing about this in the 1960s. It's not new to the kinds of technologies we have now. We will have these bonds with things. That's how people will choose to interact with them, and we ought to understand what we're doing when we're creating those kinds of bonds and not disappointing people. One thing I'd say about the Japanese, I mean, it's actually more a celebration of this object that they loved and they cared about more than a funeral for the dog. It's kind of a part of their Buddhist ritual. And they have a much more sort of broad view than we have about the difference between biology and machines. They kind of view machines as living. I was interested that The Observer had an article about Japanese robot dogs written by the religious correspondent. And he said, actually, is it that daft that they celebrate this object that they really cared about and was part of the family and that they loved, that it's gone to be recycled? And he thought not, and I'm inclined to agree.
Okay, great. Okay, there was a question over here. Yeah.
Thank you for very interesting talks. My name is Mehrdad Diyanati. I'm from University of Surrey, also from 5G Innovation Center. So you could imagine that my question relates to role of communications and connectivity in the quality of autonomous function, if you wish, both from the aspect that Tony presented, mostly social and psychological interaction, as well as Maria from reasoning aspects. So how do you think that the connectivity will perhaps reshape these aspects of autonomous systems in the future? Thank you.
Do you mean connectivity in terms of collaborating agents?
Collaborating or let's say having access to big data or data analytics, which seem to have some sort of potential, or great potential impact in the quality of autonomous operations.
I think this is extremely important from the point of view of future autonomy. I think Michael is, has been talking about precisely this issue, that we have to give future autonomous systems access to knowledge, and that means, enormous databases of knowledge from which they can learn some of the same associations and conceptual relationships that we as humans use. And part of that is the sort of structured knowledge that we use in planning, where we care most about models of action and the effects of action, causality and interactions between multiple parallel activities. And part of it is just understanding how the world works and how concepts are interconnected. So I think that in my own research, we're not yet looking at big data issues, but I think that the connection between what I'm doing in terms of automated planning, temporal reasoning, and trying to anticipate future effects of actions, coupled with what Michael's doing in terms of big data and having a proper, rich knowledge base and ontology for supporting the reasoning that's going on in the domain. I think that's the future from my point of view on this.
Jack, do you want to add anything? I mean, data is really important to what you do, right?
Yeah, like communication and collaboration for virtual spaces is really, really interesting. So with these input devices, we can work in a dimensionally accurate way. So I was saying before, you could have someone in London and someone in Paris, and we could work on a model, and if I'm working on something here and he's working on something here, that distance would be accurate across that space. That's really amazing and exciting to me. We can also start to work on projects, big projects together from anywhere. So I think Minecraft is just an example of this. So this is a really popular game, but the whole essence of this game is collaborative building. If we work together, we can make amazing things. And if we use these spatial ways of making things, we can make spatial things. Yeah. So yeah, I think there's huge potential for this.
Thank you. Oh, I would like also to hear Tony's opinion on in quality of social interaction and psychological interaction, because it seems to me that a sort of wider context awareness will have quite serious implication on those aspects of robotics as well. Of course, that's my view.
So I think that when we're developing these assistive and companion robots, we have to take into account that that robot is part of an Internet of Things, and it's going to be talking to the intelligent house. It's going to be able to talk directly, perhaps, to other places, to other robots. And it's going to be a massive change in how we think about robots generally, that the amount of information that can be rapidly transferred around. So you may have a relatively simple robot. Perhaps it's driving down the street, but it'll be talking via the cloud to lampposts around the corner, so it'll be able to see what that intelligent lamppost can see. And we haven't yet, I think, in the robotics community quite taken on how to do this. And there's a huge big data challenge to pool all this information and then to access it. But it's probably where it's going to go in the future. And also big privacy questions, of course, because everything will be instantly knowable from anywhere in the world, and that's quite a thought.
Okay, thank you for your question. Anything else? Okay, I'm going to use this slight lull to bring this to a close, I think. I think the things we've been talking about are very important, because our relationship with these systems ultimately will govern adoption as to whether or not we trust them, whether or not we'll use them. I used the DLR this afternoon to get here, and I find myself wondering, what is my relationship to the DLR? Which, of course, is a robot, and it's autonomous. And I think it's one of sort of warm, comfortable feeling, because it usually works on time and gets me to where I want to go. So I feel good about the DLR at the moment. But however, I hope I don't get any more intimate bonds with it as we go forward. Right. Okay. Anyway, I thought that was quite interesting, and there's lots more to talk about, and that we'll be able to do that in the reception at the end. But in the normal way, could we thank our speakers and panelists?